Welcome to the PetroPapers podcast. Say that 10 times fast. This is where you get your oil and gas intellectual stimulation by asking the technical questions. I'm Yoshi Pradhan, and with me here today, I have Mathias Carlsen and Curtis Whitson from Whitson. Today, we are going to talk about the IPTC paper and the paper description, as well as the citation of the paper is written below. I'm going to talk about Mathias and Curtis for a little bit before we get started with the paper. And give me a few moments to open this up. So this is IPTC 19775. So Mathias is a general manager of Americas and a PE consultant at Whitson, which is a global company that is specialized in PVT, gas-based EOR, and condensate reservoirs since 1988. His main area of work involves reservoir simulation and EOS characterization. Over the last 3 years, he's consulted on and supervised a wide range of projects related to PVT and tight unconventionals. He's working on gas EOR Huff and Puff pilots and field-wide implementation projects in Eagle Ford, Bakken, and Montney. He holds a MSc degree in petroleum engineering from NTNU and is a Fulbright scholar at Stanford University. Now I'll talk about Curtis for a little bit. Mr. Whitson is a professor of petroleum engineering at Norwegian University of Science and Technology, or NTNU, Department of Petroleum Engineering and Applied Geophysics. He founded the international consulting company PIRA in 1988, as well as PetroStreams in 2006. He researches and teaches both university and industry courses in PVT, gas-based EOR, gas condensate reservoirs, integrated model optimization, petroleum streams management, liquid loading, gas well performance, and liquids-rich shale optimization. He has co-authored 2 books, Well Performance and the SP monograph on phase behavior, which I'm looking forward to reading. He holds a BSc degree in petroleum engineering from Stanford University and a PhD degree from NTNU. He's a distinguished member of SPE and received twice the Cedric K. Ferguson Award and the Anthony F. Lucas Gold Medal Award from SPE. He's received the 2010 Excellent Research Award from Statoil for his contributions to gas-based EOR and fluid characterization. So Whitson was elected to the Norwegian Academy of Technological Sciences in 2012. Welcome to both of you on the podcast.
Thank you so much. Thank you so much. Good to be here. Good to see you again.
Likewise, it's great. I've been following your podcast and contributions, and enjoy being here as well.
Awesome. Well, to get started and reorienting everybody for our viewers and listeners, could you walk us through the paper of IPTC 19775, or characterizing the oil shrinkage behavior in your facilities?
Yeah, so the title of the paper is just called Quantifying Separator Oil Shrinkage. So pretty descriptive. It's a paper that Curtis and myself put together for IPTC last year in Saudi Arabia. And it was essentially based on 2 observations that I think both Curtis and I made when we worked with a wide range of companies, not only actually in conventionals, but also in conventional assets as well. And the first thing is that a lot of times the rates from our wells are typically measured at separator conditions, and in many cases they actually seldom reach stock tank conditions on a single well basis. Further with that, a lot of the engineers that use this type of data many times doesn't actually realize that they're using the separator rates in their analysis, which always will actually make your well look much more, or at least will over predict the performance from a oil perspective in every single case actually. So with those kind of practical observations, we wanted to see, first of all, under what circumstances is kind of appropriate handling of separator shrinkage important, and then following up from that, how can we actually then use, in cases where it is important, how can we use an equation of state model to calculate or estimate separator oil shrinkage factors on a daily basis, such that we get consistent rates to work with that are all kind of these delicious stock tank rates that makes things consistent. So that's kind of the paper in a nutshell.
Awesome. I was excited to read the paper because that is a question that we consistently have in terms of how we can influence some of our separator conditions to make sure we're getting everything that we need at the stock tank. One of the interesting points that you mentioned in the paper, as far as using a consistent shrinkage factor, is that the error for that shrinkage factor could be as high as 20% when we don't take into account the separator conditions. And I wanted to know, how is that so? And is there a correlation between your fluid type and then the amount of susceptible error? For instance, the more solution gas GOR a fluid has, the more susceptible you are to error.
Yeah, and that's of course a very good fundamental question in this setting. And I think at that point it can make sense to take a step back and just define what is kind of separator oil shrinkage. And it just when you're separating oil and gas at the surface, when you're producing typically from an oil well or a condensate well or a wet gas well, those conditions are much higher than the conditions, or they're different than the conditions where we're actually selling oil and gas. So from those separated conditions to typically stock tank conditions, there's a process that we refer to as separator oil shrinkage, where gas is coming out of solution and the separated oil is shrinking in terms of volume. And then to your two questions, there is, first of all, is it relevant for all fluid systems, or does this error of not accounting for it, is that dependent on fluid system? And the answer to that is yes, in capital letters. The first thing there is, you can take a simple example like a dry gas well, which doesn't have surface liquids. Of course, then separator oil shrinkage, it doesn't make sense to talk about it. But in any case where you're producing or separating liquids at surface, it will be to a smaller or bigger degree important. And there, what we communicate in the paper is that for very, very low GOR fluids, where there is just not that much gas in solution in the first place, so not that much gas in solution to potentially come out of solution from the separator to stock tank, then it won't matter that much. So in general, that's, if you deal with dead oils or black oils or low GR fluids, doesn't matter. But then as you get leaner and leaner, the more important it is. And adding to that kind of complexity is of course also the separator conditions themselves is very, very different if you're dealing with low separator conditions, as you're doing in many parts of the Permian Basin, many parts of the Bakken, Scoop Stack, and the Montney, where from the separator condition down to stock tank, the conditions are not changing necessarily that much. While in other basins where there's typically, or at least in the areas where there's much higher in the initial reservoir pressure, the separator conditions tend to be also much higher, especially in terms of pressure. So there we are typically dealing with Eagle Ford, the Duvernay, other some parts of the Permian there as well, where you get a much higher separator pressure in particular, and then also typically an associated separator oil shrinkage factor, which is much lower, which means that the oil is shrinking more, so the shrinkage is more severe. So that's kind of that in a nutshell.
No, thanks for that clarification, and thanks for clarifying, especially with the relation between your leaner fluids and then your lower GOR fluids as far as the shrinkage factor, the range changes. The other question I had was, when reading through the paper, I noticed that in the discussion section you were talking about when conducting your gas cycling EOR. So how can one take into account that shrinkage condition when they're conducting that GCEOR?
Yeah, so that's also a very good question, and I think in the context of this paper, it was mentioned as one of the cases where you would typically expect changing shrinkage factors over time, just because the compositions that you're producing are changing so dramatically. especially when you're dealing with gas huff and puff EOR. What we've seen through several studies, some of it is also published, is that the producing compositions, or the producing GORs, if you like, even just through a very, very short call it puff cycle or production period, is changing a lot. And when compositions are changing a lot, that also means that in many cases, keeping everything else the same, your shrinkage factors will also or can potentially change a lot. So that's why it's important to account for it, which makes call it the accounting in gas huff and puff EOR much more challenging than just for primary depletion. But the way we do it in practice, kind of the key, no matter if it's gas cycling EOR or if it's just doing primary, the first thing to do is to have some methods where you use the measured rates at the surface and the associated separator pressure and temperature, together with a properly tuned equation of state model to then predict the composition. And then once we have the composition, we then flash that composition down to the separator conditions, where we take the separator oil and flash again to stock tank conditions. So there you have a separator oil volume, and you have a stock tank oil volume, and just the difference between the two of those you use to calculate the shrinkage factor. And this is something you do on a daily basis, and something that you can do in different softwares, including Whitson Plus.
Awesome. I really appreciate that clarification on what you can do, especially for gas cycling EOR. And that's been a hot topic as far as taking into account your PVT when doing your gas cycling EOR and its applicability in our unconventionals. And that really does. And thanks for emphasizing that importance of that PVT, of that testing for GCEOR. You mentioned briefly, and you already mentioned this when answering a previous question, or one of the first questions, in terms of just the relative differences of shrinkage factors. Could you provide a range of those shrinkage factors when you have different fluid types? For instance, in black oil, what are those ranges of those shrinkage factors? What are we looking at for volatile? And then what are we looking at for retrograde condensate?
Yep, so that makes sense. And maybe before that, just defining what the separator shrinkage is. So the separator shrinkage is just the stock tank oil volume divided by the separator oil volume. So that will always give you a number below 1. So for different kind of the simplest cases will be the edge cases. So as I mentioned already, the dry gas, shrinkage factor is not relevant. For dead oils, it will be 1 because there's essentially no gas coming out of solution. And also for black oils, it will be very, very close to 1 typically. And that's also going back to why you see, for instance, black oil correlations from standing and whatnot doesn't actually take into account separator processes or separator conditions. Which makes sense because it's not very sensitive to separator conditions in, at least if you compare it to more volatile systems. So, black oils, you're typically looking at something north of 0.95. And then once you get into the volatile oil region, you get more gassing into solution, there are critical fluids, condensates, and wet gases. It can really, be anything from, we've seen down to 0.6 actually, and all the way up to 0.9. And there, it's a combination of the fluid together with the separator condition. So it's a combination of those two that kind of determines the magnitude, whether it's 0.6 or 0.9. But that range is pretty wide and very, very hard to kind of generalize.
Awesome. Right. And I know I asked that question because I think of what are some of those hard and fast numbers to take into account, and just also show some of our viewers and listeners that significance of shrinkage factors as you're going through your separator, you're going through your facility, of how much of a change your PVT can make from where you're measuring, and how important it is of where exactly you're measuring your PVT from. So
you bet. And on that note, in the Bakken, for instance, where it's mainly black oil, or in the Midland Basin where you're you're a guru yourself. There where it's mainly these lower GOR fluids, at least if you compare it to the Delaware Basin and the Montney and Duvernay and some of these other places that has the entire gamma of compositions. There it's not as important to deal with as in at least on an absolute basis if you compare it to some of these more complex basins in terms of fluids.
Awesome. Now I have an interesting question for you because, well, I'm a fan of data collection and I'm a fan of just looking into some of the PVT data and what can be done with PVT data. But I also know that not everyone can collect the PVT data or know the significance of the PVT data. So how much PVT data is needed at minimum to develop an EOS model that is field wide? Because you've mentioned about this too, of how it can be applicable to the field. And say a black oil reservoir, because I'm mostly involved with black oil, how many I mean, the thought I had is, well, how many samples do you need to take per square mile?
Yeah, and that's also a question we actually get a lot, and I'll also let Curtis chime in here, but I'll give my 2 cents on that. So first, yeah, kind of that, what's the minimum number of samples you need to create an equation of state model? So obviously, the minimum would be one sample, but typically that's not what we recommend. We recommend to use all the data you have in a particular basin to work with. And in that sense, it's always the more the merrier. And in the Permian, we've had a PVT, call it the joint industry project with now close to 20 companies where we have more than 100 different PVT reports both through the Midland Basin and the Delaware Basin, and that gives you a basis to create a very, very, very robust field-wide equation of state. And in the context of these field-wide equation of state studies that we've done all the way over North America in all these unconventional basins, then in every single case we've had more than 20 PVT reports. So that's more like a rule of thumb number that you can probably use just in terms of at least what's provided very good answers for us. The second question there in terms of how many samples per square mile is also something that we get a lot. For me personally, I'm not that worried about number of samples per square mile. What's more important for me would be to go in and look at the GOR range in the area of interest, whether that's a basin, a field, a county, or call it several pads that you're interested in, and making sure that instead of being too fixed on number of samples per square mile, making sure that if you span GORs from 500 to 3,000, you make sure that you have a 500, 1,000, 2,000, and 3,000 type of sample instead of just picking 5 ones that are in the 500 GOR range. So that's my 2 cents on that. Curtis, maybe you want to chime in with a comment there.
Yeah, I mean, obviously, if you're looking to use an equation of state for a very limited purpose, for a single well or something like that, then you can get away with maybe a single sample. But who's really doing that? And the thing is that in these basins, the fluid properties can vary very considerably. And so we've been doing this in conventionals for the last almost 30 years, that where you have variation in producing GORs, APIs, and potentially totally non-communicating systems, but they're from maybe a common source. Then a single equation of state being able to handle all of those fluids in a consistent way, both initially for initial fluid in place calculations during depletion, and then potentially in gas EOR type projects, is a great use because you have the single model. You get a lot of mixing within the reservoir, within well bores from different parts of the reservoir. And so having this single model to handle all of those fluids and all the mixtures of the fluids, it really requires to build the model around a wider range of fluids. And in the tight end conventionals, with the exception of the Bakken, I guess, you have everything from very lean gas condensates to lower GOR oils and kind of everything in between. So if you really want to try to have a robust EOS model that can handle all those types of fluids, then you need, at least 10, 20 samples, but not of a particular GOR, but the entire range of the GOR, the entire range of the APIs. So you're doing more of an interpolation if you come with new samples, new wells into that model, then you're doing extrapolations, which is what you would do with a single sample.
I really appreciate that clarity, Curtis and Matthias, because yes, you definitely need to interpolate, or it'd be much better to interpolate some of the data and taking into account the ranges of GORs that is experienced in the field, as opposed to guessing something that is out of the scope or out of the range of the EOS model. Well, I was thinking a lot about the paper as far as application goes and understanding your shrinkage factor in different parts of your facility. And I was wanting to get your thoughts on what kind of setup in the field you envision where shrinkage factor is captured at different parts of a facility. And then if you have a tool that can connect to SCADA to obtain that shrinkage factor at different points in the facility.
Yeah, so in short, there I think, or at least in general, and also what the paper discusses is that you have measurements at a separator, whether that's a single well separator or whether that's a common tank battery where there's a lot of wells feeding into it. At least if you have a way to estimate the composition of what's in that tank, it's kind of from that tank where the material balance is 100% honored, because you're capturing all the gas and all the oil across that separator and down to stock tank. That's kind of the exercise that we're trying to deal with. That data, it typically comes from SCADA systems. Some companies have this standardized and or data-based and easily available. Some companies we work with, where they want to do this calculations on a daily basis, they have to work with their data acquisition team to make sure that this data is data-based properly. But in our experience, at least, the data is readily available, at least if you have a wellhead meter and a wellhead separator. And in times where you don't have it, this exercise is not relevant either. And what we do is just, it's very simple. You just have the separator rates and separator conditions over time, which you can get from, for instance, a SCADA system. And then you combine that with a properly tuned equation of state, and a tool that can convert those rates into compositions and calculate the separator shrinkage factor on a daily basis. And we have a tool for that. There's also other softwares that have tools to do that automatically.
Awesome. Well, glad to know that there is a solution for that too. And I had another question in mind, especially the questions that we get relating to primary infill wells. And I've done some internal work in terms of determining the causes of higher GORs, and we found that infill wells tend to have higher GORs than your primary wells. So how can we adjust the calibration determining shrinkage factor when you have a primary infill well situation and an infill well has a higher GOR than the primary?
So it's that's a very hard question to I guess answer in general. But what you know when you get and you see this all the time where infill wells has higher GORs, that means that the composition of what you're producing is leaner than what it was, call it in situ and maybe the parent well. So in general, everything else being the same with a leaner fluid system, you should expect that the shrinkage is a little bit different. But also complicating that further, if the surface process or the separator conditions are also different, that can kind of make that go kind of both ways. So in general, keeping everything else the same, maybe there will be a slight difference in shrinkage factor, but that of course also depends on how much higher or how much leaner that GOR is. So that's kind of the boring answer, unfortunately, to that question.
Right. It really does depend. And it also does depend on what kind of fluid properties you have, because obviously in a volatile fluid or for volatile reservoir fluid, that difference between the infill and the primary GOR might be higher compared to the ones that are in the black oil.
Maybe I could just make a comment to that. I mean, basically, if you really want to do this accurately, you need to take into account for a given well or an infill neighboring well to the parent. But basically, for any well on a given day, you need to take into account it's got a producing GOR, an API, and a set of separator pressure and temperature. All four of those changing, or all four of those will, in a sense, come into calculating correctly the shrinkage factor. And the way we're doing it, at least the way we try to do that, is that we try to make sure that on that day, we find a composition with the equation of state that will reproduce what you're producing from any and every well in terms of API, producing GOR at the particular separator conditions. And when you find that composition that gives you kind of an exact description of that fluid on that day, then you'll be able to take that and flash it down to stock tank conditions with that composition and feel pretty reliable stock tank volumes are going to be calculated. So I think that's the key. And part of this process that we're using is the ability to come up with these compositions for any given well in a basin, for example, as a function of their producing GOR, API, pressure, and temperature. That's really the key, and it's maybe the tricky part if you're just going to try to do it without that type of software and approach.
Awesome. Thank you so much for that. There's another question that I had that was relating to reservoir simulation. And because I'm a reservoir engineer, I just had to ask this question because I get these comments quite a bit in terms of rel perm curves. And I've noticed that in the paper, the tables that when putting for the inputs for the simulation, the Corey exponents, for instance, that was used for the compositional reservoir simulation were reused. I was curious if that is appropriate to use for unconventionals in determining rel perm curves, and why are you using those exponents?
Yeah, so here, just for context, we show in the paper a few compositional runs, and the only purpose there is just to get some different fluid systems produced over time, where we get some changing well stream composition or some changing GORs over time, and then we can use those compositions to run the separator shrinkage factors calculation over time. So that's just a kind of a tool for us to get these changing compositions over time. So in that sense, at least from what I'm concerned, in the context of separator oil shrinkage, it's not necessarily that important, but we can probably go through it anyways. And I think the first thing to mention, and Curtis have also a few cents on this, is that rel perms in compositional reservoir simulation models are extremely difficult to handle consistently. And Curtis can fill in some blanks there. As I mentioned, in the context of what we're talking about here, it doesn't really matter, at least in my opinion, what we use, because we just want to get some changing compositions over time. That said, since actual measured rel perm curves are close to non-existent in unconventionals, I'll be very surprised if folks have very strong opinions on what to use versus what to not use, as there's so little data on exactly just that. So that's kind of my two cents on that question. But Curtis, maybe you can chime in with a couple of cents.
Yeah, again, I agree with what Mathias is saying. In terms of the shrinkage factor issue, you have a producing GOR, you have a producing API at a given set of separator conditions, and that's coming from a lot of different things, including the multi-phase flow into the wellbore, which has rel perms, viscosities, and so forth, controlling what producing GOR is. So there is a connection there, but the point is that you need a good estimate of your well stream composition for whatever reason it's there, to get the shrinkage factor right. And then going to this reservoir side of your question, yeah, there are essentially no rel perm curves available for individual wells, certainly. And even basins, there's very few out there that are published, maybe companies that are sitting on them. But, they're there. They're in principle should be the same for black oil and compositional reservoir simulation models. And what I think Mathias was alluding to, that you have this problem of, and sometimes in compositional reservoir simulation models, where you don't know which phase the mixture is. Okay, if it's a gas or an oil phase, and according to whether it's defined as a gas or an oil phase in your compositional model, will determine which rel perm curve to be using, because we give in gas, oil, we give in oil, water, and so forth. So you kind of need to know the label of your phase. And in these fluid systems and many of the tight unconventionals, you have basically near critical like mixtures where you don't know if it's an oil or gas. So that causes extra problems on top of not knowing what the exponents really should be.
Thanks for talking about some of those limitations, as well as some of the complexities, especially with the compositional reservoir simulation, and what should be the key takeaways for the compositional reservoir simulation that we should get out of in determining our shrinkage and the different ranges of shrinkage too. I have one last question for both of you, and you've already answered this in a way with bits and pieces of it when I asked different questions throughout this podcast. And I remember there was a 2012 paper that Curtis, you wrote, as far as some of the best practices for your PVT, for PVT collection and for PVT analysis and in unconventionals too. But for the sake of our viewers and our listeners, and in the context of the paper, I want both of you to answer some of the best practices for separator and facility conditions to make the most out of determining fluid properties.
Yeah, I think this is a perfect question for you to answer, Curtis. So so the way I interpret this question is just when you're collecting PVT, what's important from a facility standpoint to get as accurate compositions carried out to the lab. So Curtis?
Yeah, I mean, we generally look at the question of why to collect samples first. And there's two primary reasons. The one is to get data from the laboratory for the producing well stream of a well, and make measurements of typical measurements of PVT properties on that sample, and then to develop the equation of state around that. Okay, so it's PVT data with a known composition, which becomes a piece of the puzzle in building that equation of state model. And for that purpose, getting a sample that supposedly represents exactly the in situ fluid, it's not so critical. Okay, and in fact, you may not have a single in situ fluid, and you probably don't. Throughout this large well box, you probably have a mixing of many different fluids of a variety of GORs. So you're getting some kind of an average composition. And over time, the contribution from one part of the well box is going to change over time versus the other part, which will cause some of the GOR changes that you see in the well. The point is that you collect samples. The key should be getting good data. You want to take your samples, and you want to get good compositions from the laboratory and good PVT measurements from the laboratory is the most important thing. And not say, well, is this really the sample that represents the entire well box of volume? Because it probably doesn't. So in that case, you get the samples. We talk about it in the paper. And of course, the earlier you can get those samples, maybe the better chance they are of representing the initial in situ fluid or average in situ fluid. And there's nothing wrong with that. It's great if you can do it, but it's not critical as getting good quality data. Now, getting good quality data, that depends on which laboratory you go to, who's managing the laboratory over time. It's this consistency of the laboratory procedures, but also the execution of those laboratory procedures. So getting good compositional data and good PBT measurements to go with those compositional data, that's at the top of the list for doing it right. And then again, the second thing is that if you're in an area where you see different GORs in different wells, as soon as you step out and start seeing a significantly different producing GOR in a new well, then you can justify getting new samples for that. So you're trying to cover this variation in compositional space when you build that equation of state. So you don't want to just take samples from all of the low GOR wells only. So that's I think a general comment. And then some of the gory details are discussed in that paper you mentioned from 2000, I think. Gosh,
Yes.
I don't remember, 11 or 12. So
11 or 12. And I'll put that paper citation as well in the description box for our YouTube video and for the podcast. Well, those were all the questions I had to ask to just pick your brains for both of you. So thank you so much for answering all my questions.
Yeah, and thanks for the invitation. It's been a lot of fun. You do a great job as always. Thanks.
yeah, it was a pleasure. And I sincerely want to say thank you for doing this on your spare time. And it's really a great thing. It's a great thing to see the enthusiasm that you bring to the technical side of our industry. And so it's been a pleasure being here.
Awesome. Well, you guys heard it from Mathias and Curtis on all the questions that I peppered them with regarding IPTC 19775. This is Yogeshri Pradhan, and I am signing off.